Cool, so everyone, thank you for coming. This is the first one, I think the first Rust Meetup in set for a few years now, I don't know. Woo! Yeah, so I'm excited. I think I want to do more of these, to be honest. I don't know, do you think you're going to come like monthly?
Yeah.
Yeah, okay. So we're going to do the monthly. That's great. So
let's make all the AI ones.
Yeah, so, by the way, unfortunately, DoorDash messed up the pizza order, so this is all the pizza we have. But let me know if you want me to order more, and I'm going to get some like another vendor or something. So apologies for that. What else? We're Svix. We do web extending as a service. We love Rust. I've been personally using Rust for many, many years, even before Svix, but we only use Svix with Rust. I only use Rust with Svix. And yeah, we have like 3 great speakers today. So the first one's going to be Micah from Cloudflare.
Cool. I think we got this. Thanks everyone for coming. My name is Micah. I'm a principal engineer at Cloudflare, and today I'm going to be talking about how we do dynamic code loading for user-defined functions in Arroyo, which is a SQL-based stream processing engine built in Rust. So first, a little introduction to Arroyo. It's a SQL stream processing engine. Basically, this means that we can do stateful computation, things like aggregates, window functions, joins, over streams of data with results materialized in like tens or hundreds of milliseconds. These computations are fault tolerant. There's a consistent distributed checkpoint algorithm under the hood that stores the state of this computation on a periodic basis. It's able to roll back in case of failure. It's been very scalable. You can run really small. What we're about Rust is that you can run a Rust process that has 5 megs of RAM and can kind of scale down to that size, and also can scale up and run in a distributed fashion to tens of millions of bits per second. We were a startup. We got acquired by Cloudflare 6 months ago, and this is now the underlying engine that supports a product called Cloudflare Pipelines, which is a stream processing as a service product. But it's also open source, and the rest of this talk will be basically about the open source Arroyo engine. So first, for people who aren't in the kind of like SQL query engine world, what are user-defined functions? Well, SQL is a programming language, and it's a pretty powerful programming language. It has expressions and functions and stuff. But sometimes you need a little bit more than what SQL kind of gives you out of the box. Maybe you need to like parse some internal binary format. You need to reuse existing business logic, implement like custom applications. You might want to like call out to an external system, like a database or another service. Form like ad hoc joins across different data sets that don't necessarily fit inside of your main engine. Or if you're like a tiny startup trying to build a stream processing engine, it's really helpful to allow your users to extend it in various ways, because then you don't have to build all the functionality anyone might want. So UDFs basically let you extend a SQL engine by providing functions that can be called as normal SQL functions. Arroyo is built on top of a SQL framework, query engine framework called Data Fusion, which some of you may have heard of. This is, I think, one of the most successful kind of Rust infrastructure projects. It's, I wouldn't say single-handedly, but contributed to the fact that almost every new query engine or database that's been built in the last 3 years has been built in Rust, as opposed to previously Java or C++ or Go. And we use it for various parts of our kind of SQL support, including our planner, which kind of turns raw SQL text into a structure called a logical plan, and then applies optimizations on it to make that SQL more efficient. And then we also use the expression engine, so the thing that actually evaluates the SQL code. So in Data Fusion, there's native support for user-defined functions. It basically follows this interface. You give it a name, a signature, which defines the arguments and the return type. SQL is extremely flexible. It is not at all like Rust. You can have all sorts of crazy signatures, including periodic arguments. You can support various different types. It can be totally unstructured. And this signature enum basically lets you define all those things. There's a return type, what's the data type that it returns. You may notice this also takes in the archetypes because the return type may depend on the type that is passed in. So if you have like a count on a number type, it might be an int or a big int, or sorry, like a plus, depending on the thing that's passed in. And then there's this invoke function which actually calls it on the data and returns the result of evaluating this function. Data fusion is entirely based on Arrow, which is a columnar data format that has also sort of taken over the analytical data world in recent years, and I would say Rust has the best or second best implementation of it. So if you want to actually implement this for a particular user-defined function, you write some Rust code to implement this trait. Possible no one can read this, but please sort of get the idea. But we find the signature, the return type, and then in this example, we're converting a number to hex. So pretty straightforward to implement that. Actually, the implementation is not quite in here, but you can sort of imagine what that does. So if we're a stream processing engine and we want to allow our users to write user-defined functions, well, maybe one answer is we just give users, this interface that we had here. There's a couple problems with that. Number one, that interface is really complex. It requires users to understand a lot about SQL that they probably don't really want to know. They have to be able to write these kind of like vectorized functions across these columnar formats, and deal with like the Arrow RS interface, which is like pretty complex. Nullability in SQL is really, really complicated and has a lot of esoteric rules and important semantics. So yeah, I mean, basically, you don't really want people to have to like write all this stuff. Just do something really, really simple. So the rest of the implementation. Whereas, like, if you're a Rust programmer and you want to write this function, like this is what it looks like, right? It's really simple, just to take a number and turn it into a hex string. But Data Fusion makes you do all this stuff. Second, and arguably bigger problem, and the one that's the focus of this talk, is that UDFs need to be statically compiled with the engine. So just to set this up a little bit, this is like kind of the Arroyo interface. If you want to kind of play around with pipelines, create these streaming jobs, you can go into this interface, you can type your SQL query, for the UDFs, you can write your UDF code in here. We basically want an experience where you can just like, hit this preview button here. We're going to compile the UDF for you, and we're going to load it into the engine. But if we actually want to do that, it means we need to A, ship Rust C with the engine so that we can compile the UDF dynamically. And then we actually have to like compile our entire engine just to load in your UDF, right? This, for a large Rust project, we all know compile times are not a strong suit of the Rust programming language. And so, like our engine has like 1 million lines of code, plus all of the, I don't know, tens of millions of lines of dependency code. And so this takes many minutes, even if you have a really powerful machine. And this is like a really bad user experience if people are trying to like play around with this stuff. Or even for deploying these for real, you have to basically have this really complicated caching and compilation infrastructure to make this like reasonably performant. So instead, we want to be able to dynamically load user-defined functions. We want to basically compile just a little bit of code that implements the user logic and then load it into our engine dynamically. Okay, so how do we do that? There's a few different options if you're kind of thinking about this problem holistically. One option that's pretty straightforward is you kind of embed some other dynamics engine, for example, a Python interpreter, a Lua interpreter, V8, whatever it is, and you basically just like stream your data into that. You let your users write these UDFs in that programming language, and you evaluate the result. Alternatively, you could run like a separate container, have some kind of like RPC protocol that connects out to that container, sends the data, gets back the results. This is the approach used by a system called Beam, if anyone's familiar. Third option that seemed very promising when we started working on this stuff, and has since become less promising, I think, is to use WebAssembly. This has a lot of nice properties. We can compile Rust to WebAssembly, compile many other languages to WebAssembly. We can even share memory and just like give it access to the actual data, let it execute its logic, and then use the results. Unfortunately, this has a lot of kind of downsides from a user experience perspective. Users have to really be aware of like the limitations of what can be compiled into WebAssembly. Only some libraries will work. Lots of surprising things will not. Like time doesn't work in WebAssembly. And for other programming languages, besides Rust, it's even more limited. So you really need users to become experts in like exactly that set of trade-offs. Then the fourth approach here, which is one that we eventually took, is to compile the code into a shared object or dynamic library on the operating system, and dynamically load that into our Rust process. This is great because it's normal Rust. You can just basically treat these dynamically loaded functions as if they were compiled into your binary in the first place. You just pass it data, you get back results. It's fast, there's no overhead. But there is a problem here, which is Rust does not have a stable ABI. If you don't know what this is an application binary interface. These are the rules about how do we lay out pointers, how do function calls work, how do we represent various types, how do we structure structs, like how exactly are the fields laid out in memory, how do we pad them. And Rust basically is not committed to a single set of rules that they basically are going to keep forward indefinitely. And that basically means that if you compile a shared object with one version of Rust, and you compile your host application with a different version of Rust, they will not link in general. This is, it's surmountable maybe if you're really, really careful to always have some kind of like shared compilation infrastructure where you're always going to compile your engine, all your shared objects with the exact same version of Rust, compiled in exactly the same way, running on the same operating system, the same type of CPU, same microarchitecture in some cases. But it's not really great for like shipping an engine to users and expecting them to be able to load their different functions. So the answer is very old. It comes from the C programming language, which we all hopefully are familiar with and choose not to use because we're Rust programmers. The problem is Rust doesn't have a stable ABI. The solution is, well, C has a stable ABI, at least on most operating systems. It's sort of become the like lingua franca of systems programming. Everyone can expose a C API, and everyone can consume it. And so basically, instead of exposing Rust, we're going to expose C. So we have this like C-compatible interface that wraps our user code. And then that basically gives us a method that we can call that is a C method. And our host could just call that. Because it's all across the C API, it's all standard. We can guarantee that it will not change. Any version of Rust will work correctly. Unfortunately, the C API is very, very limited compared to what we're used to from Rust. There's a bunch of rules we have to follow in order for this to all work. One rule is that all of our structs have to be marked with this repr_c annotation. Only some things can be marked with repr_c. Basically things with primitive types, pointers, C-compatible enums, which are enums that also basically transitively follow these rules, compatible structs, which all their fields are repr_c, and then slices with certain limitations. So basically you can't just like throw any Rust object over the wall. you have to explicitly construct your data that you're going to use in these interfaces to follow all of these rules. Third rule is that all of our functions have to have this no mangle annotation that have to be marked as extra in C. And basically what this does, Rust has a process called mangling, which if you're familiar with C++, you've also seen. In order to implement modules, we need to make sure that in the final binary, none of our symbols have the same name. So mangling is basically a process of giving a unique, distinct name to every thing that exists in the final binary, even if you have like a two-string method on one struct, a two-string method on another struct. When we compile them, they have to be distinguished. When we're calling them from C, we need to be able to call them from an actual name, like in this case, add. And so the no mangle annotation says we're just going to include this in the binary exactly called add. The fourth and very, very important rule is do not panic. Panics are a Rust language feature. They invoke a lot of Rust machinery. And depending on how you have them configured, they will unwind the stack. And that does not work across a C foreign function interface boundary. So you have to be really, really careful with all of your code that gets loaded, not to panic. It's particularly challenging for user code because users don't necessarily follow these rules. But there are some solutions for that we'll discuss. So yeah, I mean, in a nutshell, how do you build a plugin system for Rust? You first define your structs and your enums with these FFI compatible types. You define your interface as a set of functions that are marked extra in C and with the no mangle annotation. Then you compile your plugin with this special cdylib create type. It basically says to create a C dynamic library. And then from your host, you just load your .so or .dll or macOS calls them. From your host, there's a few different crates that will do this for you. We use the deal open to crate. So just to give you a little sense of like how this works inside of Arroyo. This is what our plugin interface looks like. We have this run argument, which is kind of what you call to run the UDF. This is the kind of like top level method. It takes these FFI arrays types. So again, we can't just use normal Rust types when we're calling a C library. So we have to decompose the vec into a C compatible struct. And this is basically what this is. It's exactly the things that you have in a vec, which is a raw pointer, a length, and a capacity, just decomposed into our own C compatible struct. And then we have here a tuple struct that just has like it's called array and a schema, which fortunately the ArrowRS library already has these FFI compatible types, so we just use those. And then we have basically our own result. It's just a Rust result type, again rewritten in this FFI compatible way. From the host, this is sort of what it looks like when we implement that Data Fusion UDF interface. We have this invoke method that actually calls us on the data, and we basically just turn that into a set of calls onto our UDF that we've loaded using the dealopen2 library. All of this is obviously unsafe because we're dealing with raw pointers, we're dealing with C libraries that could do whatever to memory. So we have to wrap it in that unsafe call. But the end result of this, all this work that we've done internally, is that users get to write this really simple function. It's just exactly the logic they want in normal looking Rust. They can use somewhat limited types, but aside from that, they can just write whatever code they want. And we have this little macro that generates all of that code that wraps it in the C ABI for them. So yeah, basically how this macro works, it basically parses the signature that the user writes, it figures out all the types, it figures out how to translate those into SQL types that get registered with the SQL system. It handles like the complex nullability behavior of SQL by basically using optionals appropriately. and then it generates wrapper code that does the conversion between the Rust types and the FFI types, so that users don't have to like reconstruct these arrays manually. And then, crucially, it also includes a standard panic catch and wind around all of the user code, so that we're able to catch any panics that the user might produce and send them as errors across the FFI boundary, so we make sure no panics escape. And that's basically it. Yeah, I mean, this is sort of what it looks like. It's a lot of code, but yeah, basically does all the stuff I just talked about. And then from an architecture perspective, this is sort of how we structure it. We have a compiler service that does embed Rust-C. The web UI basically sends the code to an API or sends the code to the compiler service that produces the shared object. It gets written to object storage and then loaded dynamically by the workers when they're trying to execute these pipelines. So, one more detail that I'm going to skip, but I just want to say, at Cloudflare, we do a ton of Rust. The whole data platform that I work on, the streaming engine, the Iceberg catalog, and distributed query engine is all in Rust. We're hiring people to work across this whole stack. Also for a bunch of other things, including like cool network stuff and proxies and all sorts of things. So if you're interested, please come up and find me. And thank you.
We'll do like 5 minutes of questions, maybe even less, and then we're going to go to the next speakers. Any questions, Micah?
Yeah. Can we go through the slides you skipped? I'm really curious.
TLDR. Yeah, TLDR, basically, how do we do async functions via this FFI boundary stuff? And then how do we do Python?
So you're going to speak again the next
Yeah.
Thanks.
Cool.
Are you doing any static analysis to guard against people writing UDFs that read empty password as a side effect, or?
No, so all of this is sort of like self-hosted by companies. So it's their own engineers who are writing this code. If you were offering this as a service, you definitely would need to probably honestly find a different approach that doesn't rely on just loading random user code. But if you don't have those security concerns, there's nothing that's going to be faster than just loading actual code and calling it within the process boundary.
So you showed a little bit the sort of diagram where like it looks like the compiling is happening as a service sort of hosted as part of your thing, which seems like it mitigates many of the concerns you had at the beginning about like using the unstable Rust API, because in fact you are compiling the code and like can make sure you use the same compiler settings.
Yeah.
But it also prevents users from doing things like import depending on arbitrary cargo crates, and like unless you're sort of giving them a full file system and like things to play with there. Talk a little bit about sort of the trade-offs of like sort of who compiles this code, whether your customers want to do that or you want to do that, and how that interacts with the choice of the FFI.
Yeah, so maybe the distinction here is that, so we distribute the system primarily as a Docker image,
okay.
And everything, like the compiler included, are part of that Docker image. At least that's the simplest version of this. So in theory, we could be really careful and distribute exactly the compiler that we use to compile it within that Docker image. And if people just kind of stuck to that, that would be okay. But it's pretty brittle in practice, especially as people potentially have like multiple versions of this running across their infrastructure. You have like the control plane, the compiler service that's like updated, but not all of their workers have updated. So I mean, I think it is possible, especially if this is your own system that you're running, to orchestrate it in a way that mitigates at least some of these issues. But if this is something you're providing, like as an open source project, then it's going to be run in a lot of different environments in different ways. It's really hard to like make that work consistently.
So you then provide compatibility guarantees about the API boundary yourself as well. Then, like you're locked into keeping that sort of trait. Yeah.
So that well, the code at least, like a UDF written for version X should compile for version X+1. The internals can change eventually, but so like how that macro works, for example, can change and has, but the user code should always still work.
Great, thank you.
Cool, so another round of applause. right, next up is James from Svix. He's going to talk about using Clickhouse from Rust.
Alright, cool. I'm Nathan. I'm going to be talking about a database of sorts that we built recently at Rivet. It's a geo-distributed, low-latency, high-throughput KV database based on Epaxos, which is a mouthful, but I'll get into it. We're building Rivet. It's an open source library for long-running jobs, so timely manners, like a lot of AI agents are long-running tasks, and we power those. You can also do real-time docs, workflows, a bunch of other use cases that you can't really do with stateless workloads. For the distributed systems nerds, it's a globally distributed actor system, very similar to durable objects or virtual actors in Orleans. And the key point is multi-region. One of the big things that we offer is low latency actors at the edge, which enables a lot of things like multiplayer, collaborative documents, and local first sync. But running multiple regions and anything in multiple regions is a real pain, mainly because distributed consensus is really hard, and cross data center requests is the highest source of latency. Rust is fast, but speed of light is actually quite slow. So the problem that we have, the reason that we went out to go build another database, a mini database, is that each actor can be addressed by a key. So every single actor has a string, and that string needs to be universally unique to a single actor ID. And so we need to be able to handle conflicts of multiple people trying to reserve the same key at the same time across multiple data centers. So for example, say a user signing up with a username, whatever, two different data centers, you need to be able to say, hey, only one of you can have this actor ID. So here's a small code snippet from Rivet. We have a function called getterCreate, and we pass in this key right here. So how do we know there's only one actor with the name Ferris while minimizing round trip times? So this is where the fun begins, because there's a lot of different types of consensus, and I'm going to walk you through the types of things that we had tried and did not work out, and how we ended up with Epaxos. So our constraints is we need to have equally low latency to all regions, so we can't have a single leader data center that holds a source of truth to the world. If we did that, then say it's in US East 1, everything on the other side of the world would be really, really slow. We need to have high throughput and low contention rates. So by that I mean we assume that we need to be creating a lot of actors really, really fast, but it's not often to have contention with multiple people reserving the same actor name. And then consistent and partition tolerance. I'm going to talk a lot about RTT, round trip time, in this talk, because RTT is really the unit of how slow is your system going to be on this given consensus algorithm. So for reference, about one round trip around the world is about 400 milliseconds, and one round trip to a core of data centers with a lot of asterisks is about 200 milliseconds. This will make a bit more sense in a second, but this is the number that's helpful to really base everything on. So the first thing we had tried, this was the V1 of our product, was having a single leader data center that stored all of our actor names and all of our actor keys. This is great if you are in the same data center, but if you're on the other side of the world, reserving an actor name is going to take, at worst, 400 milliseconds. Also, this creates a single point of failure, as if that one data center goes down, a lot of bad things happen. So next we tried to look at Raft, which many of you may have heard of. This is what the entire HashiCorp stack is set up on. So if you've ever set up something on Console or Nomad, you're setting up a Raft server across multiple servers. Raft is great because it's easy to understand, but in terms of latency, when you're running nodes in different regions, it's really, really slow. So not only do you have a single leader, so you have the same problem we had in the previous architecture, but now you also need 2 extra round trips to all of your followers to be able to write anything to the log. So if we reserve an actor ID, at worst, we're going to be seeing a 600 millisecond latency. And the last bit, I really don't like Raft. I've seen too many outages with Raft. It's like the #1 source of outages in Roblox is the Hashi stack. It's not fun. What also doesn't work is multi-Raft. Multi-Raft, it powers CockroachDB, Yugabyte DB. This works by taking Raft and having a bunch of smaller consensus, but it still shares all the same problems with Raft in terms of latency. Next up is Epaxos. This is the other really popular consensus algorithm you'll see. There's a lot of variations on it. There's a lot of debate over what's correct and what's incorrect. This is out of the scope. But the TLDR of this is that it takes about 2 round trips to get a consensus in Epaxos. So you're going to have a proposal phase saying, hey, I want to reserve this actor key, and then an accept phase of like, okay, now I own this actor key. And that's going to be about 400 milliseconds worst case. So after a lot of searching, we eventually ran across something called Epaxos, which was proposed in 2013. And it's an extension of Epaxos that adds a optimistic pre-accept phase. What that means is that instead of having 2 round trips for each, for the proposal and the accept, you can actually add a series of dependencies of other proposals that this depends on to have an optimistic accept phase. That means that if there's no contention, so only one person asks for an actor key, then the latency is going to be at best 200 milliseconds, which is most of our writes. If there's a lot of contention, so multiple people are asking for the same actor key, you're going to end up with a 400 millisecond latency. So it's Epaxos with an optimistic phase. This is so this is the diagram in the paper. I'm not going to go through the full diagram, but it's a fun read. Again, every time you make a proposal, it says this is everything else that might affect this proposal. And by doing that, you're able to actually optimistically check to see if there's going to be a conflict. So this is what it looks like when you have a bunch of data centers. Now with Epaxos, we can have 5 data centers, but we only need 3 of the data centers to agree on the same actor key. So benefits, again, best case 1 round trip to the core of data centers. There's no single log, so unlike Raft where you have a single point of contention, all of the keys are actually distributed and don't conflict with each other unless you explicitly say so. Consistent partition tolerance and some availability. The cap theory is a whole different, it's a whole thing. And then the bonus is it allows complex multi-key operations. What I mean by this is that you can say, hey, this key depends on the changes of these other keys. And so you're actually able to say, have partial conflicts across some of the data set. But for our use case, we're doing simple key value sets, so we're not using this functionality. Some trade-offs, consistent reads are expensive. So if you need to know for sure that you have the right value, you actually need to write a full proposal to the log and talk to all your peers. And that is expensive. And it is not good for high conflict writes. If you're doing high conflict writes, you're basically just falling back to Epaxos. If you want high conflict writes, Raft is probably better, but it doesn't have the same low latency benefits. So we built Rivet Epoxy. This is our Rust library that implements Epaxos. And it's in the Rivet repository, and you can go check it out today. Now, when we reserve an actor, step 1, we propose, hey, I want to reserve the key Ferris to this actor ID, and this actor ID is unique. We send a proposal to all of the peers. If there's no conflict for a quorum of peers, we get our 200 millisecond round trip time. If there is a conflict, then we'll have to fall back to Epaxos and we'll have a 400 millisecond round trip time. Short side tangent, because reads are expensive, there's a lot of stale reads that you want to optimize. So stale reads are saying, hey, I have this data, it might not be right, but I can tell you for sure that this data probably has not changed. So 200 millisecond reads for each request is not good. The key here is design your data to be immutable. So you can get a strong read when you need it, but if it's not mutable, then you don't need to worry about doing reads all the time. Use cases of Rivet, obviously actor keys. We've also extended this to be part of our token and our ACL system. Tokens are very low conflict when you're reading and when you're writing those. And global configuration. So anything you say in Rivet, like, hey, I created this namespace, is actually available globally. The source code is here. You can follow me on X here. That was a lot. I'm happy to answer questions. And if you have questions about the specific algorithms, I'm happy to share a bunch of links and resources that I've gathered along the way. Go for it.
so multiple-specific algorithms, like, did you actually test and implement all of these, or did you some of them you just like discarded them because you knew the properties? Like,
Yeah, a lot of the properties, we actually had a version of multi-raft that we almost launched with, and then I was like, there's got to be something better.
yeah.
No, the Epaxos paper, I think I have it up, does a lot of investigation to what you're talking about. So they did they have a full suite which you can deploy with Terraform onto EC2 to investigate like latencies and comparisons with other algorithms. They've done a lot of work on it. So,
Nice.
yeah.
How do you test correctness of the system?
Great question. There are a lot of, if you run across the Starlight library, that is what we want to be using. We're not there yet. Yeah. A lot of smoke testing, a lot of post testing. So.
Are you persisting writes to disk, or are you just relying on in-memory storage for the consistent data?
Yeah, that's another slightly weird thing that we're doing compared to a lot of implementations of Epaxos and such. A lot of people just set it up and test in memory. We use FoundationDB under the hood, so everything is done in FoundationDB, and our nodes are actually stateless.
In general, the algorithm is basically storing a copy of the full data set in each replicated node. And we're going to handle local reads quickly, or like, what's the sort of data replication factor we're talking about here?
Yeah. So with Epaxos, if a node goes offline, it's not going. There's a system to catch up to other reads. But the idea is that we design our system heavily around immutable data. So if a node doesn't have data, it's going to try and talk to the other nodes and establish consensus. So there's a protocol in the Epaxos called a recovery protocol, which is like, hey, something might be wrong. Like, let me rerun a subset of the Epaxos algorithm to get the correct version.
Does Epaxos lose any guarantees that Paxos has, or?
The idea is that once you have a pre-accept, so there's two phases. There's a pre-accept, that's the optimistic track, and then there's the full proposal and acceptable. The pre-accept does not have any trade-offs. The trade-off is that you have to send all of your dependencies of other proposals that affect this with the request, so it's not good for high write throughput, as opposed to Paxos is a lot simpler. All right. Great.